Today we have the pleasure to hear Vincent Pilaud from École Polytechnique about acyclic reorientation lattices and their lattice quotients. Vincent, it's yours.
Okay, thank you. So thank you very much for the invitation. So I copied the link, these two links to the slides and to the preprint in the discussion. So go and play with the slides if you're bored. So I want to speak about these acyclic orientation lattices and their questions, but I think I should just start with context and a very simple one, which is just permutarbrahedra and associahedra. So I think we are all familiar in this audience about what I will talk about. So I will go a bit quick, but please just interrupt me if something is unclear. So I will start with lattices. So I play with the lattice, so a partially ordered set with mids and joins, and I will consider lattice congruences on this lattice, so equivalence relation, which is compatible with mid and joins. So my two main examples are the classical weak order on permutations. So the elements are permutations, and they are ordered by inclusion of inversion sets, and the classical Tamari lattice on binary trees, which I order by path of right rotations. So let me show what are the cover relations. So on the left, the cover relation corresponds to switching two consecutive positions. And on the right, the cover relations correspond to the right rotations that we know very well. And what interests me in this talk is that there is a connection between these two lattices, and this connection is a quotient connection. So you have a congruence relation, which is called the Sylvester relation. So it's just an equivalence relation on the permutations, so that if you contract the congruence classes, then what you get is a Tamari lattice. So you have several ways to understand this congruence. So what are the congruence classes of the Sylvester congruence? So let me just show you on an example here. So you pick a binary tree, and I will tell you what are the permutations which correspond to this binary tree. So what I do is that I label the binary tree in order, and then I consider this binary tree as a poset from bottom to top, and I looked at all linear extensions of this binary tree, and these are the permutations that you see on the left. So you have to put 1 before 2 before 3 and 4 before 3, but there is no relation between 4 and 1, 2. So it gives you these three permutations. So this is a Sylvester congruence. So what is interesting here is that you have a connection between these two lattices. So now let's do the same at the level of polytopes or geometry. So let me remind you about fans and polytopes. So I will work with fan. So fan is a collection of polyhedral cones, which is closed on the faces, and so that any two of these cones intersect along the face. So here is an example of a fan. So you take all these cones. One of the cones is missing is a cone with just a point 0. It should be there. These cones, they glue together nicely and they form a fan. And what you see on the right is the inclusion poset on these cones. So now let's look at the dual object. So the dual object is a polytope. It's a convex hull of a finite set of Rn, or equivalently bounded intersection of finitely many half spaces in Rn. And we're interested in the faces of the polytope. So the intersection with supporting hyperplane. So here are all faces of the cube. You have two-dimensional faces, one-dimensional faces, and then the vertices, which are zero-dimensional faces. And on the right, what you see is the inclusion poset or reverse inclusion poset on the faces of the cube. And as I said, there is a duality between these two things. So when you have a face of a polytope, you can associate to it a cone, which is a normal cone of this face. So the positive spine of the orthonormal vectors of the facets containing this face. So for example, for this red edge here, I look at the two facets containing this face, so the red and the orange one. And oops, my computer think this is interesting. So the red and the orange one, I looked at the normal vectors, and the cone generated by these normal vectors is the normal cone of this edge, red edge. So for each face, you have a cone, and you look at the normal fan of the polytope, which is a set of all normal cones of all faces of the polytope. So now what you see here is the inclusion poset on the cones, or the reverse inclusion poset on the faces, and these are just the same poset. It's a lattice. Okay, so now that we're on the same page on fans and polytopes, let me look at two fans. So on the left, you have the bread fan, which is a fan with one maximal cone for each permutation. And this cone is given by all the points whose coordinates are in relative position, in relative order given by the permutation. And on the right, you have the Sylvester fan with one maximal cone for each binary tree. And the cone is the inequalities of the cones are given by the let me show on this picture, by the edges of the tree. So if you have an edge from I to j, then you put the inequality xi smaller than xj. And again, there's a relation between these two fans, and this is a gluing relation. So you obtain the Sylvester fan by gluing, starting from the bread fan, by gluing the cones, the maximal cones, which corresponds to permutations in the same congruence class, in the same Sylvester congruence class. Okay, so now this translates at the level of polytopes. So you have two polytopes. One is a permutahedron, the convex field of all permutations in 1n. And the other one is the associahedron. So it's a convex field of points associated to trees. The coordinates of these points, I don't really need them. These are the coordinates given by Pilaud. And there is still a very nice connection between these two polytopes. For this, you have to look at the inequality description of these polytopes. So the inequality description of the permutahedron is the following. So this first H is a hyperplane given by sum of the coordinates equal to constant. So of course, when you permute the coordinates, the sum is constant. And then you have one inequality for each subset, proper subset of 1n, which is given by this this inequality. And on the right, you see that you have the same inequalities, except you don't look at all proper subsets. You only look at intervals.
Vincent, excuse me, there's a question in the chat by Darius Greenberg. Can every fan be obtained by taking a hyperplane arrangement and combining chambers?
Yes, you can look at your fan, and then for each wall, you take the hyperplane containing this wall. And this gives you a hyperplane arrangement, and then you remove the walls you don't want by gluing cones together. So you can do that.
Thank you.
Here it's a very special fan that we start from. So a very special hyperplane arrangements that we start from. So the story will not go that well, but yes, you can do that. Thanks, Dominique, for mentioning the question. Okay, so what I was saying is that you have the associahedron has less inequalities somehow than the permutahedron. So that means that you can obtain the associahedron from the permutahedron by just deleting some inequalities. So you just delete the inequalities that you don't want, so the ones which do not correspond to intervals, and you obtain the permutahedron. So as a video, it gives you this. So you start, let me start again. You start from the permutahedron, and then instead of deleting the inequality, let me push it to infinity. And what you get is so let me start again. What you get is an associahedron here in blue, and if I keep going, I get a cube. We'll speak about this cube a bit later. Okay, so and here is a connection between the geometry and the lattices that we mentioned. So let's look at our polytopes, so the permutahedron or the associahedron, and let me just look at the graph of these polytopes, and I will orient this graph in a linear direction. So this direction goes from the identity to the reverse of the identity, and for the associahedron, it goes to the left comb to the right comb. It's the same direction actually. If you do that, then what you see as an oriented graph is a Hasse diagram of the weak order that we mentioned before. and on the right, what you get is a Hasse diagram of the Tamari lattice. So there is a very nice connection between this the geometry and the lattices, and this is what I will try to generalize in this talk. So just before that, let me put a non-slide. Just because I know that you love Malvenuto-Rothenauer and Loderon algebra, and what I want to say is that this very same connection between the permutation and the binary trees gives you the connection between the Malvenuto-Rothenauer algebra and the Loderon algebra. So I don't want to enter the details of this slide because we won't speak about that. Okay, so now before I go to acyclic reorientations, I want to go a little bit deeper in the lattice theory of the weak order. And this is this follows work of reading. So what I want to do is I want to use the fact that the weak order is actually a semidistributive lattice. So let me explain what is a semidistributive lattice. So a lattice, we've said, it's a poset with two operations, a meet and a join. And actually, you can forget about partial orders and you can just keep the meet and the join. So you can think of it just as an algebra with two operation, meet and join. And if you do that, then it's very natural to ask when are these two operations distributive? And we call it, in this case, we say the lattice is distributive. But this is a very strong condition. So here on the left, you see a distributive lattice. It's a very strong condition, and we sort of weaken it a little bit by asking for joint semidistributivity. So we say that the lattice is joint semidistributive if this distributivity condition holds in the case where this happens. So if x join y equals x join z, then I would ask that the distributivity holds. In this case, these two things are the same. So I can just write x join y, or I could just write x join z. This would just be the same. Okay. So I ask this for this condition, for this distributivity in this very special case. And for some reason, these semi-distributive lattices are very important. And I will say that the lattice is semi-distributive when it is both joint semi-distributive and mid semi-distributive. So the same, but with the dual condition. So why is that interesting? Well, you probably know that when you have a distributive lattice, then you can represent it as a lattice of order ideals on its poset of joint irreducibles. Another way to say that is that you can represent any element as a join of joint irreducibles. And these are exactly the joint irreducibles which are below y. When you have a semi-distributive lattice, you cannot quite do that, but you can do something similar. You can represent any element by something which is called a canonical joint representation. So here it's written in a bit complicated way. Let me just explain you what is a canonical joint representation. So joint representation of an element y is just a way to write y as a join. So, well, one way is just to take y. Y is a join of itself. But you want to look at all possible ways to do that. And the first thing that we would do is that we would just keep those representations which are redundant, meaning that I don't want to have a sub-representation which still represents y. So I look at irrelevant representations. And among these joint representations, these joint representations, I can order them by inclusion of their order ideals. So I say that j is smaller than j prime if anything which is in j is below something which is in j prime. And I would call canonical joint representation of an element minimal irredundant joint representation of y if it exists. Does not necessarily exist. So here are some examples. So for example, this green element on top, I can represent it as the join of the atoms. This is the best way that I can do. So the best means that I want to have it as low as possible. Here, this green element, I can represent it just as these two, as a join of these two. And this is the best that I can do. Let me show you an example where this canonical join representation does not exist. This example here, the element on top, I can represent it as a join of x and y, or the join of x and z, or the join of y and z. And these three representations, I cannot compare them. So this one is not semi-distributive, but when you are semi-distributive, then you have a very canonical way to represent each element. So it turns out that the weak order is semi-distributive, and I will explain you what are the canonical join representations in the weak order. So I look at a permutation. So we have said that the weak order is the set of permutations ordered by inclusion of inversion sets. And we already mentioned that the cover relations correspond to descents. So I just want to exchange two elements. So I have something below me, let's say. I want to exchange two elements which form a descent, and then I go down. So a descent, so I have to explain you this picture. This picture is a table of the permutation, but because of Jean-Louis Laudet, I represent the table by writing the positions here and the values here. So I represent sigma I instead of I sigma I. It's important to represent trees. Okay, so here is a descent. It's two consecutive, so the positions are here. So it's two consecutive elements, and the first one is larger than the second one. So now what I'm saying is that the join irreducible elements, so the elements that I cannot write as joins of things, are the elements with a single descent. And if I want a permutation with a single descent, then well, you tell me this descent, and then I have no choice. I mean, I have to put all dots which appear, all values which are before the smallest value of the descent, I have to put them before. All values which are larger than the largest value of the descent, I have to put them after. And then in between, I have some choices. So anyway, this is a canonical, sorry, this is a join irreducible. So it's a permutation with a single descent. And so what I'm saying is that when I have a permutation sigma, then I can, to each descent, I can associate a permutation with a unique descent. So all the dots which were before, I put them before here. All the dots which were after, I put them after. And then in between this descent, I looked at the dots which were below the red edge, and I put them increasingly. And I look at the dots which were above the red, and I put them increasingly after. So I associate to a permutation and a given descent of this permutation, I associate a join irreducible, so permutation with a single descent. And reading proves that the canonical join representation of sigma is just given by all these join irreducibles. So you look at all possible descents, and you construct this canonical join irreducible for each descent, and you do the join of it, and this is the canonical join representation. So let me illustrate it. So for example, we said that this green reverse permutation is just join of these three. And I have done it here. So I pretend that if you compute, you take this permutation and you do the pictures that I did before for these three descents, then what you get are these three permutations. And I have done this example as well. So this permutation here has two descents, and this is the reason why it's join. Its canonical join representation has two elements. Okay, so now what we said is that from a permutation with and a given descent, we can associate a join irreducible. And I already told you, if I want a join irreducible with that descent, I mean, this is encoded here, but I can encode it in an even simpler format, which is called an arc. So what I do is I take this picture and I shrink it horizontally so that the arc is allowed to bend, but it's not allowed to pass a vertex. So it gives me this picture. So in other words, an arc is something which goes from A to B. A is the smallest element of the descent, and B is the largest element. And it has to pass above the element in capital A, which are the elements which are below in this permutation, and below the elements in capital B, which are the elements here which were above this red edge. So I can encode this this permutation with a single descent. I can encode it with an arc. I can also encode an arc with a quadruple, which is just left points, right points, the points which are below and the points which are above, right? So these are the arcs. And what we said is that we can, from a permutation, we can look at all its arcs. And this is said that this is exactly the canonical general representation of this permutation. So let me do it directly because I think it's quite nice. So look at the permutation. So this permutation 2, 5, 3, 7, 1, 4, 6. So draw the table of this permutation. As I said, the positions are here and the values are here. And now draw a green arc for each ascent and a red arc for each descent. And now you shrink everything down. So you shrink everything vertically in such a way that the arcs are allowed to bend but not to pass vertices. Then what you see in red is, well, you can think of it as just a bunch of permutations with a single descent, so a bunch of joint irreducible. So it's a canonical general representation of this permutation. And what you see in green is a bunch of permutations with a single ascent. So it's a set of meet irreducible permutations. And this is a canonical meet representation of your permutation. So it's just an encoding of this canonical general representation and canonical meet representation. And now let's just think of this encoding combinatorially. So what do we see here? We see a bunch of arcs. They are not allowed to cross. The reason is that they were not crossing here, and I just shrink them without creating any crossing. So this is the second condition. And the first condition is that, well, you cannot have two red arcs which start from the same left endpoints or finish at the same right endpoint. Well, just think of it in this picture. It would mean at that point, you will have two red arcs arriving. So you will have two descents arriving at this point. It just doesn't make any sense. So this is called a non-crossing arc diagram. So non-crossing arc diagram is a set of arcs which are non-crossing, and you don't have two with the same left endpoints or two with the same right endpoints. But you can have some which have the same left, and you can have someone which has the same right endpoint as the left endpoint of another one. So this can happen. It's perfectly valid. It is in the case where you have two consecutive ascent or two consecutive descent. And this is an encoding of the permutations. So these are bijections between permutations and non-crossing arc diagrams, and the reason is really lattice theory. The reason is that this is just an encoding of the canonical general representation of each permutation, and the weak order is semidistributive. So when you have a semidistributive lattice or a joint semidistributive lattice, then you can construct what is called the canonical joint complex. So it's a complex whose ground set is a set of joint irreducibles, and the faces are the canonical general representations. So for each element in your lattice, you just compute the canonical general representation and you represent it in your canonical joint complex. And so reading proves what we discussed before, is that the canonical joint complex of the weak order is isomorphic to the non-crossing complex on arcs. So non-crossing means non-crossing arc diagram. So non-crossing, no two same left endpoints and no two same right endpoints. So I have represented this this complex here. You can check that this complex has 24 faces. So it has one face, which is the empty face. It corresponds to the identity. It has, I don't know, 3, 7, 11 joint irreducibles. Then it has, I don't remember how many edges. And then it has one face, which is this triangle, which corresponds to the top, the reverse permutation. And we said the reverse permutation is its canonical general representation are the 3 atoms, and this is the case here. It is the only permutation which is represented by 3, which has 3 canonical journals. Okay, so this is just you can think of it as a representation of the permutations. Okay, so now we have done everything I needed on semi-distributive lattices. I just needed to do a little bit on lattice quotients. So so now what we do is that we take a lattice congruence of the weak order. So lattice congruence, again, it's just congruence, an equivalence relation which respects meets and joins. So if you compute meet or joins, it should not depend, the class in which you arrive should not depend on the representative that you have picked in your two classes. So when you have a lattice congruence of a lattice, then it turns out that each class is an interval. So you see here that my bubbles are, well, in this case, are very simple. They are just small snakes, but they are intervals. And it turns out that the lattice quotient is isomorphic as a poset as the subposet of L induced by the minimums in your congruence classes. So here, what you do, you keep all permutations, which are the minimums of those classes, and you look at the induced subposet, and what you see is a Tamai lattice. So here is the Sylvester congruence. And even more, this quotient, if L was a semidistributive lattice, then the quotient is again semidistributive. And the canonical general representations in the quotient, you can think of it as just the canonical general representations in your lattice that only involve John irreducibles, which are minimal in their classes. So let me explain that here in this picture. So for example, we remember that this reverse permutation is the join of the three atoms, and in the quotient it will still be the case. So this permutation is minimal in its class, and its canonical general representation would still be these three minimums in the class. While this one, we remember that the canonical general representation of this element was 2314 and 1423. And since 1423 is not minimal in this class, it turns out that the join of these two elements will not be a canonical general representation, because it will be a canonical general representation in the quotient, because it will not be minimal in its class. So the fact that this one was not minimal in its class implies that this one is not minimal in its class. So what I'm saying, so here is the theorem. So what I'm saying is that take a lattice congruence of the weak order, then look at the joint irreducibles which are minimal in their classes. And while we know that the joint irreducible permutations, we can encode them by arcs. So let me consider this set of arcs. Then what I'm saying is that the quotient, so the quotient of the weak order by the congruence is in bijection with non-crossing arc diagrams, which only use the arcs in this set that I have picked. So let me tell you an example. Let's look at the Sylvester congruence. So the minimal elements in the classes, there are those which avoid 231, and oops, sorry, what did I do? There are those which avoid 231, and in particular, the arcs which are minimal in their class, they correspond exactly to the arcs which pass above all the points. Only the arcs which are not allowed to pass below a point. So you are only allowed to pass above a point. So the non-crossing arc diagrams, they are in this class, they are non-crossing arc diagrams where all arcs pass above the points, and these are also called non-crossing partitions. This is the way you can see non-crossing partitions as canonical joint representations in the Tamai lattice. Okay, so now I have told you, so this is a theorem we had before. So if you want to understand the quotient, you just have to understand what is this set of arcs which are minimal, which are joint irreducibles minimals in their classes. And well, this depends, of course, it depends on the congruence. For each congruence, you have such a set. But I can tell you when a set of arcs is of this kind. When a set of arcs is the set of arcs of a congruence. And the condition is that it has to correspond to an upper ideal of the forcing order on arcs. So this is the forcing order on the arcs. So let me tell you combinatorially what it means. So I say that an arc AB forces CD. So the red arc forces the green arc, because the endpoints of the red are in between the endpoints of the blue, and the red and the blue, I mean the red follows the blue in between A and B. So they blue and red in between A and B, they pass above the same points and below the same point. So this is the forcing order. Now you pick any upper ideal in this order, and this will correspond to a lattice congruence of the weak order. So let's look at an example. Let's look at the ideal of upper arcs. So the arcs which only pass above points. So they are not allowed to pass below a point. So it's actually the upper ideal generated by this big up arc. And this corresponds to the Sylvester congruence that we mentioned before. So here is a picture of all possible upper ideals of the forcing order. So this means that each vertex in this picture is a lattice congruence of the weak order. And the order between the lattice congruence is refinement. So when you have two congruences, you can look whether the classes of one are all contained in classes of the other ones. So this is refinement. So it's not really all congruences; it's all congruences which contain in the upper ideal of arcs. I always want these ones. It's for some dimension reason. So it's just a subset of the congruence, but I call them essentials. These are the only interesting ones. So I said each point here corresponds to a lattice congruence of the weak order. Let me show some examples. So on the top, it's a set of all. I have taken all possible arcs. So which means I'm allowed to take as a canonical general representations. I'm allowed to take anything. So it means I'm doing no quotient. I still have the weak order here. So it's the quotient of the weak order by the trivial congruence. Here in blue, I have taken only up arcs. So this is the Sylvester congruence. When I do the quotient, I get the Tamari lattice. In purple, what you see is set of down arcs. So it's the anti-Tamari lattice. In orange, what you see is a set of up arcs and the set of down arcs. So it's the join in the congruence, in the lattice of congruences is the join of the blue and the purple. And it's a very interesting one. It corresponds to diagonal rectangulations studied by Lowe and Reading in particular. And in green, what you see is the smallest possible congruence. It's the descent congruence. So you consider two permutation equivalent if they have the same descent. Okay, so now Reading proved Reading is not cited in this slide. It's a mistake. So Reading proved the first theorem. So he proves that when you have a lattice congruence of the weak order, any lattice congruence, and you play the same game we played with the Sylvester congruence, so you glue together the chambers corresponding to permutations in the same congruence class, what you get is a fan. So with the Sylvester congruence, we got the Sylvester fan. And we proved with the Santos and then in a better way, I think, with Pilaud and Ritter, that any such fan is a normal fan of a polytope. So exactly as we constructed the associahedron, you can construct a quotientope for each lattice congruence. So let me show some examples. Well, on top you have the permutarbrahedra. We have no quotient. In blue you have the associahedron, actually Laudet associahedron. In purple you have the anti-Laudet associahedron, and in green what you have is just a cube, so the smallest possible ones. So if you like polytopes and you like Russian dolls, then it's a very nice Russian doll. It's a Russian doll where whichever path you pick in this lattice of congruences gives you a way to open your Russian doll from the permutarbrahedra to the cube. So I don't know how to realize it with wood, but I would love to be able to realize this Russian doll with wood. Anyway, so this is the lattice of quotientopes. Okay, so now what I want to do is to do the same. So now, okay, so this was the context. I realize that I'm already late, but that's all right, because what we'll do is do exactly the same on arbitrary directed graphs. So here is where we start. So we pick a directed acyclic graph, D. So it's a graph that you see on the bottom, and we look at all acyclic reorientations of this graph. So you reorient some of the edges. So these reoriented edges are in red in each picture. And you are only interested in the reorientations which are acyclic, so no directed cycle. And I order these acyclic reorientations by inclusion of their sets of reverse arcs. So in the bottom, what the minimal element is just the graph I started from, the directed graph I started from. The top element is the graph where I reverse all edges. Of course, it's a self-dual poset because I can just reverse all arcs, and this is a self-duality. The cover relations, they correspond to flipping a single arc. And this is quite important. Let me tell you which arcs you have to flip. So if you want to, well, which arcs you can flip, you're not allowed to flip any arc. Because, for example, here in the bottom, imagine I flip the bottom arc, then I would get something which is cyclic. So I'm not allowed to flip anything. I'm allowed to flip any arc which is in the transitive reduction of my reorientation. So I have a given reorientation E. I look at all edges which I cannot write as so that I cannot write a path going from from U to V, which is not UV. So each time so for example, this one is not here. So this bottom edge, I can write a path going from its initial point to its endpoint. So all those which are the only ones which which are the only directed path from their initial point to their endpoint, then I can reverse them. Of course, if I have so for this edge, I have a path from its start to its end. So if I reverse this, then I create a cycle because of this path. So the ones which I cannot write as a path, then I can reverse them. And this is called the transitive reduction, the inverse operation of the transitive closure. Okay, so I have a poset. It's a nice poset, and of course, some examples are interesting. So if I start from a forest, so if the directed graph I start from is a forest, then what I get is a Boolean lattice, just because I will never create a cycle. There's no unoriented cycle. There is, of course, no oriented cycle. And if I start from a tournament, so a tournament is an oriented complete graph. It's a directed acyclic complete graph. Then what I get is just the weak order. Well, the reason is that the tournament tells me an order on the vertices. You have a unique source, then if you remove this source, you have a unique source again, and so on and so forth. So this acyclic reorientation posets are just an interesting class of poset containing the weak order. So everything I spoke during 40 minutes is just this example of a tournament. So what we'll do now is try to do the same thing I did on the weak order and try to do it on this acyclic reorientation posets. The first thing that we want to understand is when is this acyclic reorientation poset a lattice? And the answer is actually very simple, but I think it was not observed before. So the acyclic reorientation poset is a lattice if and only if the graph is what I call vertebrate. What is vertebrate? You take any induced subgraph of D, and you want the transitive reduction of this to be a forest. So let me discuss the example on the left. So just look at the graph itself here, and you look at the transitive reduction of this graph. Well, it's all the graph. You have no way to write an edge as a path, to replace an edge by a path. And this is not a forest, it has a cycle, so this is not a lattice. And and this is a proof that it's not a lattice. These two, this element on the right and this element on the left, they have two uncomparable upper bounds, common upper bounds. But the graph on the left, if you compute the transitive reduction, then what you get is just these three edges, and this is indeed a forest. And if you do that for any induced subgraph, what you get is always a forest. So this graph is a lattice. This acyclic reorientation poset is a lattice. So this is the first thing. Actually, not only it's a lattice, but it's quite easy to compute mids and joins in this lattice. And this is based on the notion of biclosed sets. So I would go a bit fast because I'm already late. The notion of biclosed set is just a way to it's a way to characterize which are the possible sets of red edges. So I tell you a set of edges, and I tell you I reverse these edges, and this condition tells me whether this is a valid set of reversed edges. And the condition is that they have to be closed in the sense which is written here. So all arcs in the transitive closure of this subset X are also in X, and they have to be co-closed in the sense that the complement of this set has to be closed as well. So sets which are closed and co-closed, we call them biclosed, and these are precisely the sets which you're allowed to reverse to define an acyclic reorientation. And once you know this very small proposition, this is you probably know that for the weak order. You know which are the inversion sets. The inversion sets are the sets so that if you have A smaller than A, B, and BC in your inversion set, then you should have AC as well. And if you have AC and BC in non-inversions, then AC should also be a non-inversion. So this you know for the weak order. It's the same here for any directed graph. Okay, so when you know these things, then you know how to compute meets and joins. Let me remind you maybe first for the weak order. If you want to compute the join of two permutations, well, what you do is that you look at the inversion sets of these two permutations. You do the union of these two inversion sets, and you take the transitive closure of that, and this is the inversion set of the join. Well, you do the same here. So if you want to understand the backward edges, so the red edges of the join, then you just take the transitive closure of the union of the red edges of all your elements. And for the meet, you do the same, but with the forward edges, so the green edges. So here is an example. Where is this example? I take this element and that element, and I would want to compute their join. Well, on the pose set, I can. It's quite easy. It's a top element. If I just look at this picture, I look at the union of all the reds. So a priori, it gives me just these three reds. But at the moment, it's not acyclic. So I want to make it acyclic, and to make it acyclic, I just take the transitive closure of the reds. So I also take this edge for that reason. All right, so now we understood which acyclic reorientation posets are lattices, and we actually understood the meet and the joins in these lattices. So let me do a little more. Let me try to understand when are these lattices distributive or semi-distributive. So this is just a slide that we already saw. Distributive, we know what it means, and semi-distributive is a weaker condition of distributivity. So distributive is not really interesting. Actually, the distributive lattices are just the ones, the acyclic reorientation posets which are distributive lattices are just the ones for forest. So they are just boolean lattices, just very basic distributive lattices. So, but let's look at semi-distributivity. So semi-distributivity is much more interesting. So there is a very simple characterization. Again, the acyclic reorientation poset is a semi-distributive lattice if and only if the directed graph is what I call skeletal. The first thing is that it has to be a lattice, so it's vertebrate, the conditions that we had before to be a lattice. And the second thing is that it has to be filled. So as filled means when you have a directed path, joining the endpoints of an arc in your graph, then so this means somehow it's a cycle, it's an oriented cycle. So you have a path and then just one arc. Then this has to actually induce a tournament. So this one, for example, that we had before, on the right, it was a lattice, but it's not semi-distributive because if you look at this edge, this arc here, the bottom arc, and this path, then this should induce the tournament. So we have two arcs missing in this graph to get something semi-distributive. But here the example on the left is semi-distributive. So if you look at any arc and any path, I mean, any path joining the endpoints of this arc, then it induces a tournament. Okay, so now we have the semi-distributive acyclic reorientation lattices. So we are in the very same state as we were with the weak order. So we can try to understand the canonical John representations and the quotients of this very specific acyclic reorientation lattices. So let's start. The first thing is that I think let me check. Yeah, I think I'm getting a bit late. So let me just say that it's very simple to express the acyclic, so to express the canonical John representations in these lattices. So you pick an acyclic orientation lattice, an acyclic orientation E, and I can write it as a join of join irreducibles. There is one such join irreducible for each arc which is reversed in the transitive reduction of E. So each arc that I'm allowed to flip back to get down, then it would give me a join irreducible. And this join irreducible, I don't want to enter the details here, but it's very simple to express this join irreducible in terms of E. So it's exactly the same thing we did with the weak order. So remember that I showed you a permutation, and then I told you from this permutation and that descent, I can create a join irreducible permutation. It was a very simple recipe. The same recipe applies here. I mean, a very simple recipe applies here. So we have the canonical join representations, and now we want to do the same thing we did with the arcs. So the arcs in the weak order, they were just a combinatorial model for the join irreducibles of the weak order. So we'll do the same here. I would love to call them arcs, but the arcs in the directed graphs are already taken, so I call them ropes. So the ropes, a rope is just a quadruple. It's two vertices, U and V, and then two subsets of vertices which partition the transitive support of UV. So what does that mean? The transitive support, it means all the vertices that you can pass through in a directed path from U to V. Okay. So it should just remind you an arc. So an arc was A, B, so 2 points, and then a partition of everything in between. It's exactly the same. Okay. So the down triangle are the things somehow in the arc. It was a capital A, the points that were below my arc, and the up triangles, it was the points which are above the arc. It's exactly the same here, except it's on the graph instead of being on the line. So these are the ropes of this acyclic directed graph. So for each arc, so these arcs are very simple. They are very so there are there are no paths joining their endpoints. But let's look at this one. So for this arc, I look at all paths joining their endpoints. So this path here, and for each vertex, I have to choose. So for each vertex along such a path, I have to choose whether I take it up or down. So for this arc, for example, I have two possible ropes, one where I take it down and one where I take it up, and the same for this arc. Okay, and it turns out that these ropes are in bijection with join irreducibles. This is a picture, it's not that important to understand the bijection. It's exactly the same as before. The arcs were in bijection with join irreducibles of the weak order. And the canonical John representations in this acyclic reorientation lattice are in bijection with non-crossing rope diagrams. And the crossing condition is, it's a bit technical here, but it's the same condition as on the line for the weak order. We are supposed not to cross and not to have the same left-hand point and the same right-hand point. And you can write it in this way. So this W and W prime are just witnesses of the crossing. So W is a point where the first rope passes above and the second rope passes below, and W prime is a point where the first rope passes above and the second one passes below. So it just exchanges. It's a proof, somehow it's a witness that these two ropes cross. Okay, so this in particular says, exactly as we saw for the weak order, that the canonical John complex of this acyclic orientation lattice is isomorphic to the non-crossing rope complex. Oops, what did I put here? So it's the same as we saw before for the weak order. Okay, And now I think I have maybe 5 to 10 minutes left. So now let's try to do quotients and polytopes. So I look exactly as before. I look at lattice congruences of this acyclic orientation posets. So again, congruences that respect mid and joins. And remember that the only things that I have to understand which are the possible sets of joint irreducibles which are the minimal elements, the set of minimal elements, minimal joint irreducibles for such a congruence. So for the weak order, we understood it using the forcing order on arcs. So here is the same. There is a forcing order on ropes, and so for arcs it was sub-arcs, and here it's sub-ropes. So it's a sort of the same condition. So a rope uv done up is a subrope of u prime v prime done prime up prime if u and v is in between the endpoints of u prime and v prime. So it has to be one of these points, and everything which was passing like everything which is below the rope, the first rope, has to be below the second rope, and everything which is above the first rope has to be above the second rope. So exactly the same condition as for the arcs. So this is the forcing order, the subrope order, and exactly as for the weak order, the congruence lattice, the set of all possible congruences of my acyclic orientation lattice, is isomorphic to the lattice of lower ideals. So it was upper before. For some reason, I changed up and down here. The set of lower ideals in this subrope order. So if you want to choose a congruence of this acyclic orientation lattice, you just pick a lower ideal of this order, and this gives you congruence. And from this lower ideal, what you understand which elements are minimal in their classes. These are the elements which whose canonical joint representation only uses the ropes of your ideal, and you understand the canonical joint representations in your quotient. Okay, so let me just give you a family of example which is particularly nice. Take two subsets of two arbitrary subsets down and up of your vertex set, and I consider the set of all ropes of that kind, so UV down and up, so that down is a subset of all down vertices, and up is a subset of all up vertices. So if you think about that, you look at the condition of being a subrope. This set of ropes is a lower ideal of the subrope order. So it indeed defines a congruence, which I call a coherent congruence. So I should have written that on the slide, but it's not. This, for the weak order, it corresponds to what we call permutarbrahedra congruences, which I define with Vivian Pons. So one example of such coherent congruence is the example where everything is down. So I take down to be V and up to be empty. That means that my ropes are only allowed, like everything has to be below the ropes. So they are only allowed to pass above. So it's exactly what I would call here the Sylvester congruence of this acyclic orientation poset. And what I get is what I call the Tamari lattice of this graph, of this directed graph. So it's a generalization of the Tamari lattice. And another interesting example is a case where this up and down subsets say partition the vertex set, and this corresponds to the Cambrian congruences of reading, and they are particularly nice if maybe we'll have time to see why. Okay, so we are almost done. We know completely the lattice theory of this acyclic orientation lattices, and now I want to do a little bit of geometry, and it's exactly the same as before. So the only thing is that I have to replace, so it comes to, it's close to Darish's question. I have to replace the braid arrangement by something which corresponds to my graph. So I consider the graphical arrangement. So I have a graph, a directed graph, but at the moment I don't care it's directed. And I consider all hyperplanes defined by xu equals xv for each arc uv in D. So this gives me an arrangement of hyperplanes. And the dual of that is a graphical zonotope, which is the Minkowski sum of all edges EU EV for all arcs UV. So on the left, you see the graphical arrangement of this this graphs that we are working with, and on the right, you see the graphical zonotope. So again, the hyperplanes on the left, they correspond to the summands, so the edges which I'm summing on the right. So they correspond to the arcs of the directed graph. The regions on the left, they correspond to the vertices on the right, and they correspond to acyclic orientations of my graph. And the poset of regions, so I haven't told you what it is yet, but you pick an initial region corresponding to your directed acyclic graph, and you orient everything, like you orient the regions from these regions to the opposite region. So it's the same as oriented your graphical zonotope linear in a linear direction from the vertex corresponding to this acyclic to this D graph to its opposite, and what you get is precisely the acyclic orientation poset. So this acyclic orientation poset that I was looking at is just the poset of region of this arrangement. So now you can play the same thing that we were playing with the recorder. So you pick a lattice congruence, and this lattice congruence tells you a quotient fan. So you glue together the regions corresponding to acyclic orientations in the same congruence class. So I have done it here. So here is the graphical arrangement. Here is my congruence. So I have to glue together things, and here is done. So I glued together. So for example, maybe we can see this big square. So this big this class with 4 elements. There are precisely these 4 elements, and I glue them together. And what I obtain is this class, which I represent by the arcs which are common to all of them. Okay, so what I said is that you obtain a realization of this quotient lattice by a fan, and exactly as we did before, using the shard polytopes that we defined with Pilaud and Ritter, you can obtain a realization of this fan by a polytope. So this is what I want to call the quotientope for this arrangement. And one is particularly interesting is when you take the Sylvester congruence that I mentioned before for the arrangement, then what you obtain is a natural generalization of the associahedron, but for your graph D. And so it's the oriented graph of this associahedron is the Tamarin lattice for this graph D. And it turns out that you can obtain it. This is weird, but you can obtain it by deleting inequalities in the graphical zonotope. So it's exactly the same as Laude's associahedron. You can do that here. Okay, so I'm done. Let me just give you some open problems. If I have 2 minutes, maybe I do that. So the first problem, so this conjecture, I spent most of my morning preparing my talk, and I had a problem with this conjecture. So I'm not sure what to put on top of this conjecture. In my paper, it's written something, but it seems wrong. So take it with, let me change the conjecture. It's a question. The question is, can you characterize the graphs for which the associahedron is a simple polytope? So I have a natural associahedron for a graph, and it's not always a simple polytope, as you say here, as you see here. So the Hasse diagram of the Tamarin lattice is not always regular. Here it has a vertex of degree 4. But I believe that it's just a very simple characterization. In my paper, I was convinced for characterization, but it seems to be wrong. So I'm not very sure of the characterization, but I think it should be very simple. The next conjecture is that, again, a very simple characterization of the case of the following thing. Among all congruences that I discussed are the congruent congruences. I told you that these are these coherence congruence where the two sets, omega and omega down, form a partition of the vertex set. It turns out that when you construct the corresponding associahedron, you get isomorphic phase lattices. It's extremely weird. It's exactly the same as the Cambrian associahedra of Olvek and Lange. You get always the same combinatorics, even if the geometry has nothing to do, and the lattice quotient has nothing to do. So it's very weird, and I have no explanation for that. So this is an example where it's not the case. You see that these two polytopes, they don't have the same combinatorics. Actually, the one on the left is simple, while the one on the right is not simple. And the reason is because I drew it for that picture. So this one is the one which really fades. Okay, and oops. And one more thing is that when this, I told you that, oops, it's written on top. I told you that for the Sylvester congruence, you can get the associahedron by deleting faces, deleting facets in the deleting inequalities in the description of the graphical zonotope. And I believe that you can do that for all coherent congruences. So we know that for the permutarbrahedra congruences. I have no idea why this is true. It seems not easy to prove, but I don't know. And the last thing that I want to mention, it's more combinatorial. It's known that the acyclic orientation posets or the acyclic orientation graphs do not always admit an Hamiltonian cycle. The reason is that they are actually bipartite graphs, and the reason is that they are ranked by the number of reoriented edges. And the bipartition is not always even. So sometimes you have more orange than blue, like on the left. So you have no way to do an Hamiltonian cycle, just because in an Hamiltonian cycle, you pass from a blue to an orange to blue to an orange and so on. It's actually conjectured that this is so a necessary condition is that you have as many oranges as blues, and it actually conjectures that it is a sufficient condition, but this is not my question. My question is, it's known that when the graph is cordal, the acyclic orientation flip graph is Hamiltonian, and I conjecture that when the graph is skeletal, in particular it is cordal. So when the graph is skeletal, I'm allowed to do quotients, and I believe that all quotientopes admit an Hamiltonian cycle. So this is something that for the weak order, we know that all quotientopes admit an Hamiltonian path. It's a recent work by Mütze and collaborators. I believe that this is still true in this very in this generality of the graph. I think I'm late, so let me jump to the last one. It's not that important. And thank you very much for your attention.
Well, thank you very much, Vincent. So do you have some questions